we were discussing logical implication. This is how we define it. If S implies T is tautology, then we claim this implication can be replaced by logical implication. And we claim the conclusion T follows from the hypothesis S. And whenever S does not logically imply T, in that case, this is how we denote this. Okay. But when we are talking about this one, so we should be, when we are talking about the implication, we know that this possibility is always possible, like S is true with T is false. But whenever I write S logically implies T, we are saying that we do not have even a single situation in my implication where S is true with T is false. That is what the claim we are making when we replace implication by logical implication. And we discussed these two examples to understand it. Okay, and through this example we identified that we need not to look into every row of the truth table to determine whether that implication is logical implication or not. Instead, I just need to look into only those rows of the truth table where all my premises are true. In that row, we just see what is the conclusion T is saying. Even if your conclusion is 1, we claim it is a true statement. If my conclusion is false, I should claim it as a invalid argument, or I should call this logically, it does not logically implies the conclusion. And that is what we can see with the second example. Out of these 4 rows, this second row and fourth row are crucial for us. And we noted that only in the second row, my hypothesis is true. That is, all my premises are true, where the conclusion is false. So we can find at least one situation. Okay, out of the 2 situations, we can find at least one situation where all my premises are true, where the conclusion is false. So that is enough for us to claim this does not logically imply. So it is not a tautology, and this implication cannot be replaced by logical implication. Next, we discuss the definition of argument. Argument is not a new definition to us. We are calling the implication with a new name called the argument. So if the implication is expressed in this form, S1 conjunction S2 conjunction S3 conjunction and so on conjunction Sn, that implies T, then that is, we are expressing our hypothesis as conjunction of premises. Okay, so he's expecting something. So USA number 110. Why do you want the control of the session? Do you want to present something? Okay. Yeah. So our hypothesis is conjunction of premises, and we say that this argument is valid. That is, you can replace by implication by logical implication is same as saying this argument is valid. Logical implication is same as claiming the implication is valid argument. Both are same. Please keep this in mind. These are equivalent sentences. Now, so we claim this is invalid argument under only one situation, where all my premises are true. Okay, all the premises are true with the conclusion is false. This is the only situation where we claim this implication cannot be replaced by logical implication, and we also say this argument is invalid argument. In all other 3 situations, that is, if one of the premises is false, my hypothesis itself becomes false. In that case, irrespective of the truth value of T, we claim it is a valid argument. And whenever we have my hypothesis is true, that is, each of these premises is true, with the conclusion is true, even in that case, we claim it is valid argument. Okay, so we discussed this too, and also we discussed if I just consider the truth table. So how do we identify, that is, which are the rows important for us in assessing the validity of the argument? Just now I discussed with the 2 examples above. The same idea is employed here also. Here we noted 4 rows. In 4 rows, all my premises are true. In those rows, we found that even the conclusion is true. As a result, it just became valid argument. And next we discussed the validity by another way. That is, instead of handling from hypothesis to conclusion, we are moving from conclusion to hypothesis. What we did here, in these examples, we are first assuming that conclusion is taking the truth value 0, and we are supposed to show that even the hypothesis carries the same truth value. And that is what we try to do here. We assume P disjunction Q is 0, and we proved hypothesis P is also 0 here. And in this case, whenever I assume Q is a false statement here, okay, whenever Q is false statement here, we noted that even at least one of the premises is false here. Okay, that is what we noted. When P is 0, so this P disjunction Q, this becomes 0. When P is 1, negation P becomes 0. See, out of these two premises, one of the premises is false. As a result, my hypothesis becomes false. So that is what we noted even with this example. There is another way of handling the validity of the argument. Now let me just go further. Let me speak about the rules of inference. Rules of inference says that you need not to construct the truth table, and you need not to look into the all different possibilities like this. Even in this example, we took the possibility like if P is 0, R is 0, what happened? If P is 0, R is 1, what happened? We are just checking with this by choosing the truth values to our primitive statements which are present in the compound statement. That is in our hypothesis. So now I don't want to do even that. So what else can be done in those cases? So that is what we are discussing under rules of inference. Okay. So before start with this, we know the definition of argument. We can write the argument in two forms. This is the one way of writing the argument. So this is the second form of writing the argument. Okay. So now, so this is what we are doing here. So this is an argument. Now to determine the validity of the argument, we are going to use rules of inferences. Say by using rules of inferences, two things happens. Okay, first thing is, so we are going to show that we are going to consider only those cases. Please keep this in mind. We are going to consider only those cases where all my premises are true. I will just consider only these cases. And with this, I will just check whether my conclusion is true or not. If it is true, we say it is valid argument. Otherwise, invalid. And at the same time, rules of inference is going to help us in arriving at T through our premises. That is, we say that how T follows from our premises. So that can be shown through rules of inferences. Now let me list all the rules of inferences. Let me list one by one. So first one. So first one is called modus ponens. Modus ponens. Now keep this in mind. You can write our argument in this form or in this form. Here therefore T represents, T is the conclusion here. S1 conjunction S2 conjunction S3 and so on conjunction Sn. This is how we write this tabular form also. Please keep that in mind. Okay, modus ponens. This is what this statement says. This says that if you have got P implies Q is a true statement and P is a true statement, therefore Q is a true statement. We can also put it in one more form, that is in this form, that is the normal standard form. So that is this can be written as P implies Q conjunction P implies Q. So from now onwards, I am not using this notation. I am just going with the tabular form. But keep this in mind. We can always express tabular form in this form. Okay. This modus ponens is also called as rule of detachment. Rule of detachment. Okay. And you can note that this is a valid argument. Now have a look at this one. I am saying my premises are true. Under rules of inference, what I told you, our premises are always true. Okay. If P is a true statement, okay, P implies Q is also a true statement. So what should be the truth value? Then what should be the truth value of Q? Q has to be true. That is what I have written here. Is that clear? So what I have said here, I am assuming that P is a true statement. P implies Q is also a true statement. To have P implies Q is a true statement, since my hypothesis is true here, conclusion has to be true. That is what my conclusion is. Therefore Q. So this is called as the rule of detachment because I'm just using the definition of implication, nothing more than that. I'm just using the definition of implication. That is P implies Q is there here, I've just written the hypothesis with I've just kept hypothesis of this premise as one of the premise, and I've just written Q in the place of the conclusion. That's why we are calling this as rule of detachment, writing the definition of implication in another form. And you can prove this by constructing the truth table. If you want, you can just construct a truth table to determine whether it is valid argument or not. Okay. Second one. Say this all rules of inferences are valid arguments. We are considering them. We are making use of them to go further. Second one. So this is called the modus tollens. Modus tollens. This is what modus tollens is. And if people can easily guess, it comes from what? P implies Q is a true statement. Negation Q is a true statement. Therefore, can you guess what should be the output? Friends, can you guess what should be the output? P implies Q is true. Negation Q is true. The output is negation P. Please go for a try. Even if it is wrong, it's fine. So feel free in my classes. So please feel free and just speak out. So if you're finding it difficult with any concept, let me know. So I'm going very slowly. If you feel like I'm slow, let me know. I can just go. I can just make myself fast, so that I can just complete the syllabus at the earliest. And don't worry about the syllabus part also. So maybe if you're thinking like, sir, we have spent so much of time, we're still in the first module, it is not yet completed. So don't worry about that. I told it in the beginning itself. We are taking more classes for module 1 and module 3 because these two has too many concepts in it. Module 2, 4, 5 carries less number of concepts. I just need 15 hours to complete module 2, 4 and 5. From those 3 modules, 15 hours is enough. But to complete module 1 and 3, we need more than, at least 30 hours is required for me. Okay, 30 to 35 hours. So this is what I am doing. I am spending more time on this one because it is made up of too many concepts. So once if we get into module 2, 4, 5, so these 3 modules are very simple. It is made up of less number of concepts. We can be fast at that point of time. Okay. Yeah, can you guess? So how do we got this one? Modus tollens. Hello? Hello friends. Yeah, how do we got this? P implies Q is always logically equivalent to what? P implies Q is always logically equivalent. It's contrapositive, right? Yeah. So that is what I have written here. So whatever I explained here, the same is applicable even here. The thing is, so P implies Q. In this one, P is written with the hypothesis. Q is written with the conclusion. P implies Q is logically equivalent to not of Q implies not of P. So that hypothesis, not Q is written with the hypothesis and not P is written with the conclusion. So it comes from modus tollens is defined through the definition of contrapositive. And once again, you people can prove it through truth table. Next one, law of syllogism. See, these things are very simple, but if you are not with the class, you may find it very difficult later. So please try to be with the class, try to learn something. Things are very simple. I'm going very slowly. Please make use of that. Law of syllogism, people can easily guess this answer also. P implies Q is a true statement. Q implies R is a true statement. Can you guess what should be the output? Yes, very good. It should be P implies R. So this is a transitive rule. P implies Q. and Q implies R, that says P implies R, that comes from the transitive rule. Yes, thank you. Very good. Good attempt. Yeah, next one, rule of conjunction. So once again, name itself says here, rule of conjunction. So it comes from the definition of conjunction only. So this is what I'm supposed to write here. If the statement P is true and the statement Q is true, in that case, P conjunction Q is also a true statement. That's all. You can note that it is nothing more than the definition of, it is nothing more than the definition of conjunction. So whenever P and Q are true, conjunction is also a true statement. That's all. Next one, fifth one. So this says that rule of, this is called rule of conjunctive simplification. Conjunctive simplification. So name itself once again says we are talking about the conjunction, or we are simplifying the conjunction. So this is what it says. If you have got P conjunction Q is a true statement, you have P is true as well as Q is true. You can take whichever that you want. Okay, both are true. When P conjunction Q is a true statement, both P and Q are true statements. You just take whichever you want depending on the requirement. Okay. Sixth one is a rule of disjunctive syllogism. Rule of disjunctive syllogism. So when you people show some interest, we too feel like giving more information to you people. So if you people kept quiet, so we don't feel talking much. So we feel like let me just complete the things. Okay, can you give me the output for this one? Or instead of this, P conjunction Q is a true statement in which negation P is true. So can you guess what will be the output? You people know when do we have P disjunction Q is true statement? Yes, very good. Thank you. Now it is just P. Because have a look at this one. You are seeing P disjunction Q is a true statement. Let me just show you how does it work. P disjunction Q is a true statement. You are saying negation Q is a true statement. Negation Q true means Q becomes what? False. So you got P disjunction Q is true with Q is false here. If Q is false, so to have this P disjunction Q is a true statement, what should be the truth value of P? P has to be true. That is what I have written here. Out of these two statements, one of the statement is false, so other statement has to be true to have this is valid argument. Now the same thing happens even in this case. Out of these two statements, I am assuming P is false here. Obviously I am supposed to get Q is a true statement. So this is what rule of disjunctive syllogism says. And you can note that, you can just note one more point. This rule of disjunctive syllogism is not different from, okay, it is not, the rule of disjunctive syllogism is not different from your modus tollens. These two are same. These two are interconvertible. So, if, for example, if you just want to, if you want me to show you this, you can note that I can rewrite this one as P implies Q is nothing but what? Negation P, disjunction Q, negation Q is there. Is it not? P implies Q is logically equivalent to negation P, disjunction Q. Then what should be my output here? So I am saying that negation P, disjunction Q is a true statement with Q is false. Because I am saying negation Q is true statement. Negation Q is true means Q is false. If Q is false, other statement negation P has to be true. See, these two are exactly the same, but written in with different written in different forms. So it is left to it is just left to the situation whatever we have there. Suppose if we have got the implication, so in a problem, and in that case instead of just converting that implication to the disjunction, you can directly use modus tollens. And whenever the problem is given in disjunction, and if it is possible to make use of rule of disjunctive solution, use this one. When it is not possible for us to use this one, so we can think of converting this disjunction to the implication, and we can make use of the modus tollens or any other concept. Okay, but just keep this in mind that so these two are interconvertible. Okay, seventh one. Seventh one is once again very simple and very important one, and it makes things so simple for us sometimes. So this is what it says: the rule of disjunctive amplification. Okay, rule of disjunctive amplification. So this is what it says: whenever you have got P is a true statement, you just don't worry, just call P disjunction Q is also a true statement. That's all. So simple. See, since P is a true statement, and we know that for disjunction, if one of the statement is true, that disjunction becomes a true statement. So now I don't know whether Q is a true statement or false statement. Whatever may be the Q. So since P is a true statement, P disjunction Q has to be true. That's all. Like 2 is an even number. It's a true statement. Now even if I read that, even if I replace that statement by 2 is an even number and 10 is an odd number, it is still fine. Okay, 2 is an even number or 10 is an odd number. It is still fine for us because it still carries the truth value 1. So though the second statement is false, it's fine for us. It may be true statement or false statement, and Q may be a big expression, big logical expression. It may be a compound statement. It's fine for us. It's fine for us. So we can just directly claim it's a true statement because I'm considering P disjunction with this statement Q. Okay. Whenever P is a true statement, P disjunction Q is always true. Good. And the eighth one, so this is called rule of contradiction. You people have used it many times in your lower classes, this one, rule of contradiction. So this rule of contradiction says, if negation P implies goes to contradiction, then what should be my output? If negation P implies F naught, what should be my output? Say this is a true statement. Try to understand. This is a true statement. F naught is always false. Since F naught is false, what should be the truth value of negation P? To have this implication is a true statement. Yeah, negation P has to be 0. If negation P is 0, what I'm supposed to write in the conclusion place? Very good. Very good answer. That's all. If people have done this kind of problems in your lower classes, like I want to prove a statement is true, and to do that we are using the method of contradiction. And the method of contradiction says that, so since I want to prove P is a true statement, assume that P is false. So when I assume P is false, negation P becomes a true statement. If negation P is a true statement, with that you just try to prove, okay, with negation P is a true statement, try to prove something and you will just arrive at a contradiction. You will get a contradiction, so contradiction, that is F naught, that is what I have written here. You will get a contradiction and you will claim that, so we got this contradiction to, it may be to the hypothesis or it may be to the some known concept or the known principle. So and we, at that point of claim, we claim that my assumption is wrong, the given statement is a true statement. So that is what this rule of contradiction says. Okay, so we'll just come back to this one. So now along with this we have got 4 more rules of inferences, but we don't need them. We are not using them in our problems. We will just take even those 4 rules as problems itself, and we will just discuss them. Okay, so now have a look at this one. You are supposed to remember the 7 rules of inferences. These are very, very important for us. Along with the 7 rules of inferences, we are also supposed to remember, so these results. That is result number 1. You should remember these results also. That is S disjunction T. is always logically equivalent to negation yes implies T. This is one statement. Second one, yes implies T is always logically equivalent to negation yes or T. And third one, yes implies T is always logically equivalent to its contrapositive negation T implies negation yes. And fourth one, if we have got S biconditional T, so we can't handle it directly. I'm supposed to make use of the result which I gave previously with conjunction and disjunction. So S conjunction T, disjunction, negation of S disjunction T. Or if you want to use implication, you can do even that also. S biconditional T can also be written as S implies T, conjunction T implies yes. If these two are true, we claim biconditional is also a true statement. And the final one is yes exclusive or T. And this one is always logically equivalent to yes or T, conjunction, negation of yes conjunction T. We need to remember them along with the 6 rules of inferences and laws of logics. We need all these things to validate our arguments. See, the difference between laws of logics and the rules of inferences are, these are all not the logical equivalences, these are all the logical implications. I can replace implication by logical implication. We don't know about the converse part of it. Okay, we don't know the converse part of it, but the implications are true. And for this example, to understand this one, I have given few examples in the notes. I will share the notes today. I will share the notes with you people today, and people just go through those examples. Simple examples I have given to appreciate this concept. See, I am running shortage of time, so I am not discussing those examples here. Those are very simple, and people can easily understand, and people can appreciate these rules of inferences through those examples. Okay, now have a look at this 7 rules of inferences once again before getting into the problems. See, whenever we get implications, okay, 1, 2, 3. So these 3 rules comes into the picture along with contrapositive. Okay, along with implication is logically equivalent to contrapositive. These 3 rules should come into our mind to think what should be done next. If conjunction comes into the picture, we are talking about these 2. If I want to merge together, if I want to bring 2 statements together, rule of conjunction. If I just want to write the 2 statements apart, rule of conjunctive simplification. And rule of disjunctive syllogism comes if we have got a disjunction. Whenever we have got disjunction, we should think, is it possible to use rule of disjunctive syllogism? And sometimes we do not have a statement in my expression, but I just want to bring some statement in between. In that case, rule of disjunctive amplification comes into the picture. And we'll just discuss rule of contradiction a little later. We'll just come back to that. Okay. Now let me consider my first example to handle this. Check the validity. Check the validity of the following arguments. So you can frame your own examples. You can frame your own examples to handle this. So for example, for this one, I will just give you one simple example to appreciate this modus ponens. If Ravi studies, then he will pass in DMS. Okay, try to understand this one. If Ravi studies, then he will pass in DMS. This says that Ravi P is 1, which means that Ravi studied. Output is Ravi passed in DMS. That's all. So that is what we are saying here. This is how this modus ponens works. If Ravi studies, then he will pass in DMS. That's a true statement. Now Ravi studied. So I assume that hypothesis is true here. Ravi studied. So conclusion has to be true here to have the modus ponens is valid one, or the argument is valid one. So I'm concluding that Ravi is passed in DMS. That's all. Okay, like that you can just frame your own examples to appreciate all these rules of inferences. Let me consider first example. Actually, this problem is also called as rule of conditional proof. It is there in the notes. People can look into it, but don't worry about the name and all with respect to the next set of problems which we are discussing. And you can note that. So when you are doing the problems, see, when you are using these concepts in your own language, So and whenever you are using the situation in future, you can frame your own rules of inferences. For example, like when you are talking about the Laplace transformation, so you are each time you people are not finding L of e power at. You know what is L of e power at is. If I want L of e power 2t, you are directly using L of e power at to write what is Laplace transformation of e power 2t. In the same lines here also, so you can frame your own rules of inferences whenever you feel like you want to prove something and you are using some standard result again and again. So in that case, you can just give a name and you can just save it and you can just make use of it in between instead of proving the same set of results again and again. Okay, this therefore R. So this is what I need to prove. Okay, have a look at this one. This is how it works. I will show you the procedure. So this is so simple. So in the first column, you people are writing steps. In the second column, you are supposed to write reasons. Okay, let me start. Step number 1. In the first first you are supposed to write all the premises. So P conjunction Q. So P implies Q implies R. Okay, and we do not have any reason. It is my claim. I am assuming these are true statements. These two are premises. Step number 3. Now I want to proceed further. To proceed further, I just have a look at this expression. I have got P conjunction Q. So whenever you see conjunction, just you should think, is it possible to use rule of conjunction or rule of conjunctive simplification? I have P conjunction Q here. We know that P is true as well as Q is true. What I will do now, I will write P is true and my step 4 is Q is true. So this came from step number 1. Okay, so we are writing the reason. It came from step 1 and a rule of conjunctive simplification. So please don't use short forms in the exam. Okay, please write everything. So when you're in the exam, you need marks. So just don't go for any short forms. Okay. Now the role of first step is done now. So P conjunction Q, we used it. It is done. So now step number 5. Okay. Now have a look at this one. I've got 3 statements here. And it is not mandatory like you have to go in this order only. You can just go in reverse order also. You can use step 4 first, then you can use step 3. You can use step 4 first, then you can use step 1. It is left to you people. So depending on the situation and depending on our requirements. Because conjunction of statements, these are all conjunction of statements, and we know that conjunction of statements, for conjunction of statements, associative lie is valid one. Okay, now have a look at this one. So it looks similar to this one. P implies something. Okay, P implies, this P implies something, and you have P itself is a true statement here. Okay, P implies something is true with P itself is true. So which means what should be my output? Conclusion has to be true. What is the conclusion in this case? Q implies R. Okay, now I will write the reason. This came from steps 2 and 3 and he used modus ponens. Okay, now step number 6. Now the role of step number 1, 2, 3 is done now. I got only step 4 and 5. Now I got Q implies R is a true statement and Q itself is a true statement. Look at this one once again. So we have Q implies R is true with Q itself is a true statement. So once again we are supposed to use the modus ponens that says that R is a true statement here. So this came from step number 4 and 5. Okay, steps 4 and 5 and modus ponens. I am using the same first rule to prove both the results. And look at my requirement. My requirement is this only. So I will write the conclusion. This is what my conclusion is. Hence, the argument is valid one. Therefore, the argument is valid. Any doubts in this problem? This is how any problem under this heading works. Check the validity of the following argument. If it is possible to show our conclusion follows from the premises, we claim the argument is valid. when it is not possible to have my conclusion, to arrive at conclusion with all my premises are true, in that case we are supposed to claim it is invalid argument. Any doubts in this? Friends, any doubts? ಇದ್ದೀರೇನಪ್ಪ ಹೋಗ್ಲಿ, ಫೋನ್ ಮುಂದೆ ಇದ್ದೀರಾ ಹೋಗ್ಲಿ? ಹಲೋ, please respond. If you do like this, so I have to be fast. ಸುಮ್ಮನೆ ಏನೋ ಮಾಡ್ಕೊಂಡು ಮುಗಿಸ್ಬಿಡ್ತೀನಿ ಅಷ್ಟೇ. I will just complete the syllabus, that's all. I just won't mind whether you people are understanding or not. I'm spending so much of time, and if people are taking so much of time to respond, if this is the case, so it will be tough even for me to complete the syllabus. So I'm going very slowly. Please make use of it and please respond. If you are finding it if you are finding any difficulties, let me know. I know where my students struggle. So under laws of logics, under rules of inference, in both the places, you people need my help. So that's why I'm just spending time here. Okay, if you feel like things are simple, let me know. Otherwise, please respond. What's wrong with you people? Why your people are not responding nowadays? And only one student responds. Okay, and the student who responded now, thank you very much. Yeah, let me try one more example to understand this. Okay, so in this example it is P implies R. Okay, they have given P implies R is a true statement with Q implies R is a true statement. Therefore, P disjunction Q implies R is a true statement. We call this one as a rule of proof by cases. Rule of proof by cases, that is proving the result by using case number 1. That is, so case number 1 says I am assuming this is the hypothesis, I am proving this result. Next I will consider the second case. I will assume this is my hypothesis and I will prove the same result. And by just combining them we can write this one. So that's why we call this one as rule for proof by cases. Okay, we'll just prove this result by using this rules of inferences along with the laws of logics. Let me see how does it works. I'll just try even this problem for you people. People can do the next problem from your side. Okay, steps, reasons. So as I told you people, first you write your premises. P implies R. Second step, Q implies R. So this is my premise. So even this is my premise. Okay, now step number 3. You can note that we have got two implications, but none of modus ponens or modus tollens or law of syllogism. None of this will help us, because even for law of syllogism we expect P implies Q with Q implies R. Even if I use contrapositive for this one, I will get negation R implies negation Q. Instead of negation R, if I get R in this place, so in that case P implies R and R implies negation Q gives P implies negation Q for us. Even that is not the case here. So which means that we just cannot employ any of these rules of inferences. I told you that at that point of time we should think, is it possible to use laws of logics? So to use laws of logics, so we need to rewrite them. And look at this one, I need to bring P and Q together. For that, this is what I will do now. So in this statement, I will rewrite this one as negation P disjunction R. So this comes from step number 1, and the statement is always logically, the implication S implies T is always logically equivalent to negation S or T. Using the same reason again for the second step, I will rewrite this one as negation Q disjunction R. So this comes from step 2 and for the same reason. Now step number 5. I just want to bring these two together because I am expecting PQ should be written together. So for this one, I have the statement P. This is my statement P and this is my statement Q. So which means conjunction of these two statements should be true statement. Okay, negation P disjunction R, conjunction negation Q disjunction R. This is true. So from step number 3 and 4. Okay, steps 3 and 4 and a rule of conjunction. So from now onwards, I will use short forms for the rules of inferences, but please don't do it in the exam. So short forms are not allowed in the exam. So just for the simplicity, I'm just using them now. Okay. Disjunction R, disjunction R. So which law is applicable here? Very good. Distributive law. I can just take this negation R, so disjunction R outside, and we get negation P, conjunction negation Q, disjunction R. Very good. It comes from step number 5 and distributive law. And step number 7 says use De Morgan law here because I want disjunction here. Okay, this is written as negation of P disjunction Q, disjunction R. So this comes from step number 6. The role of step 6 is also over, and De Morgan's law. Just tell me what should be done in the next step now. What's your step 8? Very good. So this answer is correct. So it's told we should use in step 7. Yes, disjunction T or negation is disjunction T logically implies yes implies T. That's all. And when you are doing this problem, writing this therefore is must. So writing this therefore is must here. So without that you may lose marks, because otherwise we claim that it is not concluded in there. So therefore the argument is valid. The argument is valid one. Now I want you people to try this problem from your side. So please do this. P implies Q, R implies yes, P disjunction R, therefore Q disjunction yes. Anybody has done this? At least are you people trying this? Yeah, please try this. So just like laws of logics, people can do even these problems in many ways. So in 8th or 9th step, people can conclude this. It's quite simple only. And try to avoid using laws of logics. You should not go to laws of logics in between. You should always think of using rules of inference first, because rules of inference always keeps things simple. So once when we find it is just impossible for us to handle the problem through rules of inference, we should think of using law of logic. Like the previous problem. In the previous problem, so there was no there is no other way to handle that one. So we had to use law of logics. Anybody has got the answer? Okay, so let me do this for myself. So still doing, just can just check out, and we are still in the first two problems we are discussing. So people need to practice so people can think about these problems. If anybody has got the answer, people can give. Otherwise, let me try this. Okay. Now you can note that P disjunction R is there. We know disjunction implications are interconvertible. And I can rewrite this one as negation P implies R. So this comes from step number 3. I will write converting this disjunction to the implication, so that I can use law of syllogism in my next step, because we have got R implies S here. So P disjunction R is written as negation P implies R. This comes from step number 3, and we know that SRT is always logically equivalent to negation S implies T. Now we can use step number 4 with 2. Okay, steps 4 and 2, and you should use a law of syllogism. This gives what negation P implies? Yes. Now let me just go further now. So now roll off step number 2, 3, 4 is over now. I need to look into step number 5 and step number 1. Now just have a look at these two. I just cannot handle them directly. Once again we have a problem here. What is the problem? I have got negation P implies S here. I have got P implies Q. See, to use law of, step 5. Okay, step 5 came from this one. Negation P implies R. R implies yes. So negation P implies yes. Law of syllogism. It works similar to the transitive rule. P implies Q. Q implies R. That gives P implies R. That is what I have written. Negation P implies yes. Now I've got P implies Q and negation P implies yes. I want to put it in the same form, so that I can just, if I, instead of negation P here, if I use a contrapositive, I can bring P in this one. Negation S implies P, and that P implies something else here. So that can bring into the picture. So what I will do now, on this step number 5, I will use contrapositive. That gives negation S implies negation of negation P, that becomes P. So this comes from step number 5, and the statement is always logically equivalent to its contrapositive. Negation T implies negation S. Now negation S implies P and P is implying Q. So what does it say? Negation S implies P and that P implies Q. So these two together gives negation S implies Q. So this comes from steps 6 and 1. Okay, this one came from what? Step number 5. Okay, this step 6 and 1, and along with that I used law of syllogism again. Here I am using nothing more than law of syllogism. Okay, negation is implied Q. That's good. So I just don't want my answer. I want answer in terms of S and Q, but I don't want in terms of implication. So I can rewrite this one as what? This is S disjunction Q. Okay, this came from what? Step number 7. This came from step number 7, and negation S implies T is always logically equivalent to SRT. So now S disjunction Q is there. I want Q disjunction S. I am just writing one more step, not associative. It is what? Commutative. Associative speaks about the brackets, right? Associative speaks about the bracket. So this one is commutative. Yeah, good attempt. Thank you. Step number 8 and commutative now. So which means even this statement is valid argument. Even this argument valid. So now I want you people to try this problem from your side. It works exactly similar to this one. Same number of steps, same laws you people are going to use for this one. So please try it from your side. So this is given by this. P implies Q. R implies yes. Negation Q. Disjunction negation yes. Therefore, negation P, disjunction negation R. Okay, you can note that I just interchange the position of these two expressions with negating this primitive statements. Okay, it works in the same line, same number of steps, same laws you are going to use. Nothing more than these things.